Hello, today we're continuing in our A-level physics revision series looking at exchange particles and Feynman diagrams. In an earlier video I set out what's called the standard model, which shows all the elementary particles that we're aware of. There are 6 quarks or quarks, there are 6 leptons, electrons and neutrinos, but there is also a category, this column here, which are called gauge bosons, and they are responsible for the forces that we observe in the world today. Let's take, for example, 2 electrons. If we bring them together, there will be a repulsive force because like poles or like charges repel. But how do these electrons know that the other electron is there? There has to be some kind of information exchange so that they are aware. And we say that there is what's called an exchange of particles, or exchange bosons, gauge bosons. In this case, it would be the virtual photon that was responsible for exchanging information and is essentially what's called the force carrier. Now we are aware of 4 types of forces in the world. One is the strong nuclear force, which I described earlier. Second, the electromagnetic force, which is responsible for the repulsion of 2 electrons. Thirdly, the weak force, which is responsible for keeping the sun going. And finally, gravitational force, which keeps us on the Earth. Now, the gauge bosons responsible for exchanging information are these. For the strong nuclear, it's the gluon. For the electromagnetic force, it's the photon. For the weak force, it's actually the W plus and minus and the Z. Both of those are responsible for the weak force. And in fact, we don't know because we've never found what the boson is for gravity. We think it's a thing called a graviton. But there's no evidence for that, and for that reason, it doesn't feature in the standard model. Only hadrons are affected by the strong nuclear force. Hadrons are basically everything made up of quarks, but electrons and neutrinos do not feel the strong nuclear force. So this only applies to hadrons. Every charged particle will feel the electromagnetic force. So if you're neutral, you won't feel it, but if you've got a charge, you will. Everything is affected by the weak nuclear force, and everything is affected by gravity. Now, the larger or the heavier the gauge boson is, the shorter the range of the force that exists. So in the case of a photon, that is massless, and consequently it has infinite range. Sorry, I just noticed the sun was distorting the picture, so I've taken action to stop that. I said that the photon is massless. Consequently, because it's massless, it has infinite range. By contrast, the W plus minus and the Z bosons are extremely heavy, 80 times bigger than a proton. So they have a very, very short range indeed. In an earlier video, I explained something about the weak force. I said that a neutron can decay into a proton plus an electron plus an anti-electron neutrino. But that in fact is not quite what happens. What happens is that the neutron decays into a proton plus a W minus boson. But that W minus boson very quickly decays in about 10 to the minus 25 of a second into the electron plus the anti-electron neutrino. And a man called Richard Feynman found a way of expressing this in a much simpler way by pictures, on the basis that a picture paints 1,000 words. Feynman diagrams are used to describe particle interactions. And the rules of a Feynman diagram are that time always goes upwards. So you always start at the bottom with your incoming particles, and outgoing particles go out at the top, and the interaction takes place in the middle. So let's look at exactly what happens when a neutron becomes a proton plus an electron plus an anti-electron neutrino. The Feynman diagram says you start off with a neutron coming in, you have a proton going out, you have a wiggly line. Bosons are always shown by wiggly lines, particles are shown by straight lines. This is a W minus boson, which quickly decays into an electron and an anti-electron neutrino, and both of those go out, so they're going upwards. Everything goes upwards. And that's the Feynman diagram for this reaction. In the Sun, it's slightly different. You have a proton being converted into a neutron plus a positron plus an ordinary electron neutrino. So what's the Feynman diagram for that? Well, that will just be that you have a proton coming in, you have now a W plus boson, you have a neutron going out, and then the W plus boson quickly decays into a positron plus an ordinary neutrino. And that's the Feynman diagram for the proton changing into a neutron. How do you know whether it's a W plus or a W minus? Well, the answer is you have to decide what you've got to do with the charge. Here you've got proton with a charge of +1 being converted into a neutron with a charge 0. So you've got to get rid of a charge of +1. How do you do that? You carry it away with a W plus boson. Up here you had a neutron, which has no charge, and a proton leaving. So if you've got a positive charge leaving, it means you have to balance that with a negative boson, which is the W minus. So you just need to make sure that your charges always match. Here's another Feynman diagram that you'll need to know. This is what's called proton-electron capture. So we've got two particles coming in, a proton and an electron. There will be an exchange of information, that's the wiggly line, and what you will get going out will be a neutron and a neutrino, electron-neutrino. What is this exchange particle here going to be? Well, we've got a positively charged proton coming in and a neutrally charged neutron going out, so we've got to take away a positive charge, and that means that a W plus has to go in that direction. The W plus then meets up with the negatively charged electron. Those two will cancel and produce a neutral neutrino. And that is in essence the proton plus the electron produces a neutron plus an electron neutrino. But there are other interactions. Here, for example, is a neutron coming in with an electron neutrino. There is then an exchange particle, W plus, this time moving in this direction, and out comes a proton and an electron. The principle of Feynman diagrams is pretty much that anything that can happen does happen. You just have to make sure that the charges and baryon numbers are always conserved. Here's another one. A proton and an anti-neutrino this time. Out goes a neutron and a positron. And here is the exchange particle, and that's going to be a W plus, because the W plus needs to carry the positive charge away from the proton so that it now becomes a neutrally charged neutron. It will join up with the neutrally charged neutrino or antineutrino to produce a positively charged electron, which is of course an anti-electron. Just to write the formula underneath so you can see what's happening. In this case, a neutron plus a neutrino produce a proton plus an electron. In this case, it's a proton plus an antineutrino produces a neutron plus a positron. And finally, just to demonstrate that anything that can happen does happen, you will observe that those two Feynman diagrams are simply the flip side of each other. Here, a proton and an electron produces a neutron and a neutrino. Here, a neutron and a neutrino produces a proton and an electron. If it can happen, it does happen. Books. There are 6 leptons, electrons and neutrinos, but there is also a category, this column here, which are called gauge bosons, and they are responsible for the forces that we observe in the world today. The photon that was responsible for exchanging information and is essentially what's called the force carrier. Now, we are aware of 4 types of forces in the world. One is the strong nuclear force, which I described earlier. Second, the electromagnetic. There has to be some kind of information exchange so that they are aware. And we say that there is what's called an exchange of particles, or exchange bosons, gauge bosons. In this case, it would be the virtual. Hello, today we're continuing in our A-level physics revision series looking at exchange particles and Feynman diagrams. In an earlier video, I set out what's called the standard model, which shows all the elementary particles that we're aware of. There are 6 quarks, or quarks. Let's take, for example, 2 electrons. If we bring them together, there will be a repulsive force, because like poles or like charges repel. But how do these electrons know that the other electron is there?